give an overview of, sorry, I'm gonna give an overview of what's gonna happen in this presentation. So first, we're gonna talk about my requirements and specifications, then backgrounds and observations we made from the Carolina competition and our approach and plan for this whole school year. After that, we're gonna talk about the new CAD. There is one minor change, very minor, and we're gonna talk about a new fixturing we're gonna try to do when remaking the folk box. We're going to talk about the simulations I've completed and the simulations I plan to do. In addition, the completed testings we've done, like right after the chassis was fully welded to the last minute testing we did before Carolina, and also the testings that needs to be done. And then finally, we're going to talk about the Chief Welder's project, and our Chief Welder is Ella Petticord for those who do not know. Okay. To begin, um, a reminder for everyone, we make a new chassis every 2 years. So right now it's an off-build year in that case. So a lot of the requirements specifications carry through into this design cycle. So I will just reiterate what's on the slide. So for a high-level customer goal, it's adaptability and serviceability. For requirements, the chassis roll cage must satisfy ergonomics comfort study. The driver's foot must fit completely within the foot box and must accommodate suspension, steering, and drivetrain range of motions. The chassis must provide flexibility for CVT tuning applications as well. And then finally, for specification, the seat of the chassis shall be no more than 6 inches from the bottom of the frame, should be less than or equal to 88.4 pounds with welds and tabs, and also must withstand front, rollover, and drop impact with the factor of safety of 2. And then finally, must withstand a load of 3G in all three scenarios I've just mentioned. So I know a background and what happened in Carolina competition for anyone who didn't know, but we were able to go through S&T, but through our first round of S&T, the front of the footbox bent from our driver hitting right into a rock. It was sent back to the paddock. The tech inspector saw and was like, "Yeah, no, that's fine. You're good to go. You could compete with that." So thank God for that. So, but before we brought it back for a second round, we did take off the front body panel, added a thick metal sheet, and in theory, it should better distribute the forces just in case the footbox were to hit the rocks again. So, coming from the Carolina competition, we were thinking what is one way to have a better outcome from a scenario if the footbox were to hit a rock again. Not that, oh, we're definitely going to prevent it from happening in the future. But one of the things we thought about is tapering up the footbox. And obviously, with any frame change requires everyone's input. So we've had two footbox meetings and we made a Pugh matrix of deciding whether or not it is if we should do the taper of footbox or not. So 0 represented a taper of footbox was neither beneficial nor harmful for the subsystem. +1 represented it was beneficial, and then -1 represented it was harmful. Um, from the table, current footbox, everything is 0. That's our baseline. For the taper of footbox, you can see that ultimately we decided that there should not be a tapered up footbox due to drivetrain being negatively affected, and it was mainly for two reasons. One of them was being the differential mounting, and the other was being that the half shaft motion would be really bad. As in, if we angled up the foot box, then the U joints would also be angled and not be performing optimally. So regardless of that, in terms of this whole year, there's two things I'm really trying to emphasize on. One of them is creating a better fixturing setup for to make welding easier. So we still have to redo the foot box, like if you want to compete for the spring competition. And then in addition, something I'm really honing on is the design cycle for testing. So there's three things I'm really focusing on. So to better understand the loading on the chassis due to suspensions, to better understand the G loads from the front impact, and to do fatigue analysis on the chassis. So like, we're gonna start doing that. I have questions for all of these, so if you have answers to them, let me know at the end, but we'll get to that. Um, so to begin, for the CAD, there is a chassis change. So, and it's very minor in the sense I should have clarify what that bar was. So the bar connecting to the brake and accel pedal system should be moved up an inch. And that bar is, I hope you could see my mouse. If not, I'll clarify. It's the, I'm sorry, someone. But the bar that's being moved up an inch is basically the bar that's in between the upper front bracing members. So it is this bar member here. That has to be moved up an inch because ergonomics decided that their pedals needs to be moved forward 2 inches. When I mean by move forward, it's more closer to the nose end of the foot box. Um, so that's the minor change. And on the side, I just have all the tubes we use. 065 is our primary, and all the rest of the thicknesses are our secondary members. And to reiterate, this doesn't break any of the roll cage member rules or any of the frame rules set by Bahase. So for the chassis fixture. Now, this is something I've been really discussing with our fixture lead, Ava Burke, and also our chief welder, Ella Petticord. So one of the fixturing setup that we use when making the whole entire new frame last year was using welding blocks. The thing was we're really limited to the number of welding blocks we had. And in addition, we had to constantly keep changing the fixture depending on tubes that are being welded next. And also, as we're making new fixtures, a lot of times we have to use shims or like other random metal sheets we have to try to reach that height. So the benefits for trying to do this plywood fixture is help the welders to tack every tube in one go. So it should make welding easier for them, but also reduce the time spent on fixturing itself. And one of the ways that I wanted to make sure like ahead of time that we could actually put the tubes into the fixture boards was doing a clearance study through NX. Um, and also in the PDF slides, I included another fixture from Olin Baja to help you visualize the drawing that me and Ava made in the last slide on a chalkboard. So in what we wanted to do was do 4 fixture boards in total to help weld the entire foot box. But I did begin like an iteration of it, and this is where the other new slide comes up. So let me walk through it. So in this left side of this slide is the first iteration of what I thought the fiction could be like. But the major problem was that so we have the lateral fixturing itself. So we are able to get the steering mounting tubes, the bottom tube of the foot box. But the problem was if we were to do the horizontal fixturing tube, the one that goes through the slots in the current gray fixture board that you see right now, it doesn't really account for the angle of the suspension tube, as in that it'll be hard to manufacture that because if you were to laser cut the wood itself, it won't cut it at an angle, but rather straight up and down. So that's one of the issues that I noticed when starting to begin catting like the initial idea that me and Ava had. But the solution for that is on the right side, you can't really see it that well now that I see it for myself, but there is a bar sitting right underneath the suspension tube. And to clarify, the suspension tube is the blue diagonal tube going across the foot box. And essentially, I would have blocks underneath the tube to hold it in place. So we make sure that the angle is correct and the positioning is correct through that way. This is still in work in progress, and if anyone has suggestions in how I could like better improve the fixturing, like that would be helpful in my eyes. I think also the other thing I was struggling with is I'm also thinking about the way, so in our current lateral fixture board, there is holes for the steering mounting tube and the lateral cross member for the bottom foot box. So in theory, I'll put in the fixture board and I slide in the tubes through the holes. My concern is it might not fit through it. d depending how it's cut. So that is something I'm trying to figure out. Maybe there's another way to go around that to make sure like it could for sure slide in without like issues with fitting of any sorts. But I hope that makes sense. If there's any questions, please ask in the end. Um, so I'll begin with the simulations I've done. So this is the normal front impact, drop impact, rollover simulations that we do every year. And the load I use is 3G for each scenario. So the maximum stress found were around 17,000 PSI, 18,000 PSI, 31,000 PSI, respectively. And with the factor of safety of two, none of this is yield. And I know all of you guys know what the yield stress for 4130 is. I'll just reiterate. So with the yield stress for the 4130 is 92,000 PSI, but with the factor of safety of two, our allowable stress is 46,000 PSI. So we know it doesn't yield. Now this is the simulations I plan to do or currently working on right now. So this answers the question of how can we better understand the loading of the suspension into the chassis? And this specifically does a simulation of, we're trying to do a breakout model of the shock mounting tabs. And by doing that, we'll understand, okay, how does the load coming from the shock distribute into the chassis itself? So I think in this part of the portion, I'm just going to explain how my simulation is done, like how the setup is. There are still missing information that I need to do it, but that's still in the works. So to begin, how this is going to be done is I'll be doing a drop test FEA model of the whole entire frame. So I'll be doing the same wireframe model like the drop test FEA you guys just saw in the last slide. But the difference is in how I place the constraints, in that in the last slide, the constraints were placed on each of the nodes on the frame, and those nodes were representing where the shocks mounting tabs were placed. But instead, we have RBE2s on each side of where the shock mounting tab is. And from there, we put the constraints at the other end of the RBE2s. So the RBE2s represents the shocks itself, and the constraints are placed where the shocks is mounted onto the tab. And then finally, we're going to add forces coming into the shocks itself. That's one of the missing information that we don't have right now is what's the forces coming from the shocks. So that's something we could either find through video analysis, which is what I'm trying to do. So in this setup on the FEM model, it's just for you to understand where I place my loads. So all the loads are placed on the nodes on the frame. The constraints are placed on the shock mounting points. And then finally, there is that 3G that I use for all my other FEAs. And then with that, something I do next is do a breakout model of the shock mounting tabs. So on the right, you see the shock mounting tab. So this is the left side. And essentially, for me to do this FEA, I have to extract the forces and moments that experiences at each end of the tube. And I get those forces and moments through the drop test FEA from the last slide. So that is kind of the beginning of how I could get those forces and moments and put that into this breakout model to actually see firsthand, okay, this is what happens with the shock mounting tabs. In addition, there will be RBE2s at the point where the shocks is bolted onto the tabs. And again, there is that force from the shocks that I will add there, but we don't know what that is yet. So, and in addition to that, to how I put all the tubes of shock mounting tabs together, I use edge blend to represent the welds itself. But something I am looking into is using weld fillets to better represent the welds instead of the edge blend. Yeah. And the other one I plan, very empty slide, is to do a nonlinear plastic analysis of how that bent of the foot box was made. I honestly don't know the beginning of how to do this, but I did find a video of how this could be done. So we're gonna try that eventually. And follow the video tutorial and see how the nonlinear plastic analysis can be done on this foot box. Um, so now we're gonna actually talk about all the testing that's been done. So the first testing that was done, like literally a day after all the chassis was fully welded, was the vibrations test, which is the hammer test. So the goal of this test was to see if the chassis was made closely to CAD, since the frequencies resonating to the chassis is dependent on the weight, geometry, and stiffness of the chassis. So on the right, you see all the peaks at which it resonates at, and on the left, you see the frame itself, and um it's basically held in space by two ropes. To get these data, they use accelerometers, which is like placed in different points on the frames. For the chassis, for our results, the maximum error found was was negative 2.8%. And one of the reasons why there could be these percent errors is, for one thing, there is this from rope that is carrying the frame. When doing the vibration simulation in NX, you don't really consider this rope into your analysis. So it could be acting as a member itself. And another thing was the bandwidth of the machine was really high at the time. So if the bandwidth was a lot shorter, then it probably could have honed in more on the actual frequencies that it could measure. Um, the other testing that was done, which has been done, was the jump test. And the purpose of the jump test is that, for one thing, something to know is we've been using 3Gs for all of our FEAs, but we didn't have any data to back it up. So my goal after getting like the position was actually to find, what does this 3G exist? So with this jump test, our goal was to determine the maximum G load that the car experiences at a dynamic condition. So this is much more representative of what the driver would see in real life. So over the summer, we had our drivers constantly go go to our track in Southside, and they basically kept jumping over the little hill that we have. So through what how I did the jump test is, first we did a video analysis of it. So each time the driver would just continuously keep jumping off the cliff, and then we had our GoPro and video camera to record the jump itself. And on the left, you see an image of these circles. So marker one, marker two, and marker three. These were all the points that I've tracked throughout the whole entire jump. And essentially, from from our analysis, we analyzed like 14 videos of this. We found the maximum G load was to be 2.5 Gs overall. So in a jump test, so in a more dynamic conditions, the maximum G load that the car would experience is 2.5 G, but that 2.5 G is experienced by the back wheel. So number two is represented chassis itself, so it doesn't really experience a lot of G loads on its own, which makes sense. So the next test that we did was the drop test. So this was done right before the Carolina competition. So the goal was to determine the maximum G load the car experienced in a drop impact. The same video analysis code I made for the jump test was used for this test also. And this was following the same idea, where the front wheel was marker one, the marker two, tracker two was the chassis, and then marker three was the back wheel. And analyzing like up to like 7 videos for the drop test, we found that the maximum G load was 3Gs. So 3Gs does exist, and 3G is basically again found at the back wheel. So consistently, the back wheel experienced the most G load compared to the other markers that I've also taken measures on. For the And in addition to doing the drop impact, we also push strain gauges on the frame itself. So here we put a strain gauge on a rear bracing. So this is like the back of the car near the fuel tank. And by taking the strain gauge data, our goal was to validate the drop test itself. So on the right, you'll see the three strain gauge data we took, because we at that point we did take three um te we dropped the card three times at that point. So after that, with our strain gauge data, we did a breakout model on the frame itself. So I just isolated the joint. I just isolated this joint itself and did a 3D mesh of it. And the idea of how I got the forces and moments was the same idea that I mentioned and how I would extract the forces and moments to do my shock mounting tab analysis. So with that, from the simulations, the maximum stress was 12,000 psi, which is around the welds. And then the interstitial stress, which is the node at which a strain gauge was applied, was 1,000 psi. But from our strain gauge data, our maximum stress was found to be 578 psi. And this gave a percent error of 54%. And there is that error for one of the reasons that I think is definitely why there is a 54% error is the fact that consistently in our drop test, the front wheel always hits the ground first before the back wheel does. So it doesn't necessarily experience the whole 3G drop that we assume from our initial drop test drop test FEA. So that's one of the big reasons why I think there is that 54%. And also we don't account for the shock loading. So how does the shock itself absorb all the G's from the chassis itself? Okay. For the chassis, so this is a testing that needs to be done, which answers how does suspension affect chassis. So the goal of this test is to investigate how the shock mounting tabs are affected and how the shock loading affect the chassis. And we're going to use a wheel force transducer. So what we're going to do is do the same drop test again, but in addition to that, we're going to add a strain gauge right above where the shock mounting tabs are. And from there, the wheel force transducer will extract all the forces and moments that I would use to say, okay, now we know what loading the shocks are experiencing at. I'm going to use that loading in that simulation that I made earlier that I've explained to you guys and see, does that correlate to the stress I found from my strain gauge? So ultimately, the goal of this is for me just better understand how different loadings from all the other subsystems affect the chassis, and I think it's really important for us to understand how suspension affects chassis overall. So that's the biggest goal for the mounting tab test. And for the front impact test, my goal is to investigate the G-loads experienced by the chassis in a front impact scenario, and also further investigate how the force from the bent foot box was made. So this is one of the ideas I was thinking about. Honestly, it is a huge work in progress and something I have a lot of questions for. So for one thing, the idea is that we use the older frame, the Genesee frame, which is the frame before the frame we have right now. So that is kind of the ball of our pendulum. And then the ropes are connected to the shock mounting points of the Genesee frame. And from there we would um the forklift would hold the frame through the ropes itself. And to keep a consistent like variability for each one, I was thinking of deciding on what velocity we want the chassis to hit the wall. And then from there, we could decide on, okay, this is the height that it needs to consistently drop from. But however, I have a lot of like not concerns, but it is a work in progress. It's never been done before. And one of the things I'm concerned about is, for one thing, we're using an older frame. So one of my question was, is it really reasonable to use the data from an older frame and correlate that to our current frame right now? The other thing was there is still a lot of variability when doing this test. So it is difficult to stay consistent for each trial. And another thing is, let's say this test is helpful, like what sorts of data should I take that would make this test valuable and worth our time? What I was thinking is we could include strain gauges on parts of the foot box and then see how the stress on those parts are affected, if that makes sense. So this is really like a work in progress, and I'm not sure how this could go about it, but that's the idea with the pendulum test to really understand the front impact G load, since we have a better understanding of the drop impact G loads. I just want like another opportunity to like let's find a G load for the front impact. And now we come to the part where I present to you the Chief Welders project. So this project was initially started by the previous chief welder, Elizabeth Martin. She did this as her independent study with Professor Muir, and her goal was to just analyze the weld integrity and just better understand welding overall. So right now, the goal with Ella Petticord is to analyze welding integrity of chassis welds and tab welds. So the ways we're going to do this is have each of our welders weld as many tabs on primary tubes, so on our 065 tubes. And with each of the tab welded onto the tube, we're going to take that to the MTS machine and produce a bunch of stress and strain curve. And we're going to look at the yield stress and how did the tabs breaks, at what stress did the tabs did break. On the right, you see the first iteration of Elizabeth Martin's design. So you see there's a fixture set up here that will be well, okay, let's better explain this. So the idea was her little fixture design here would connect into the MTS machine, and then there is this rod that goes through the tube, and the other end of the MTS machine will hold onto the tab. The issue was that as they kept pulling on the tab, the actual fixture itself started to deform and stretch out. And when doing the FEA model, they did see there is this huge stress concentration around this U shape. So for the second iteration that Ella Petticord did this year is make that U shape smaller, but the same problem still occurs. And they did think of a better way of resolving that. But to give a better idea of what the actual data could potentially look like, this is a data from Elizabeth's independent study. And essentially she basically, well, in this case, she used an 049 tube and a 1018 tab. And she used the same fixture setup as before, put in the MTS machine, and then observed the yield stress at that point. In this case, I'll reiterate what she said in her notes is that the simulation showed that stress nodes near the break location was approximately the yield stress of the material. So approximately is around the same as 1018s and slightly below the yield stress of the tested piece. And the yield stress of the tubing was much higher than the yield stress seen in the simulations, which shows why the tubing did not yield or deform, but the coupon, which is the tab itself, did. Um, this is again to reiterate, it's like sort of the idea of what our potential data would look like. And then finally, for iteration three, which is a completely different fixture design, is where instead of having the fixture design that Elizabeth had in the beginning, you just have two tubes on the top, and then the MTS machine can go through those two tubes and just pull it apart, and it can now like actually put more load onto the tab itself. And the FA model still needs to be done. And one of the big reasons why I included the Chief Welders project is because for me, another thing is I really want to understand how welding affects chassis overall. So the data that we're going to extract from this could hopefully help us understand, okay, what's the actual yield stress around those welds? And is it like how just have a better understanding how welding affects chassis, since we all know how important welding is overall. And for highlights for design concerns, again, I have concerns about the pendulum testing. I'm not sure how worthwhile this testing could be, but I would love to have a better understanding of the front impact. So, what kinds of data should be taken to make these tests more worthwhile? In addition, how is it really reasonable for me to use that to use the data from the old chassis and correlate that to our current chassis? And then finally, another thing is doing more fatigue analysis on tabs and getting the load and getting the number of cycles. So, um, is there any questions? Yeah, yeah,
Really nice job. Can you guys hear me?
yeah.
So this is Harris. I was Harris Mandel. I was the chief mechanic in from 2020 to 2021. Um,
Mm,
can we can we
mm.
go back to your requirements, please?
I knew this was gonna happen. Of course. No,
Engineering
no, no.
lives and dies by the requirements.
No,
Uh,
I understand. I fully
yeah.
understand.
Well, yeah, I just wanted I didn't get a good chance to take a look at them, and I'm sure maybe somebody else in here might have questions as well.
Of course.
Uh, I'm glad to see that you guys have a weight goal. Where does that come from?
The Waco comes from our previous car. So the Genesee car was 88.4 pounds.
Okay, and you want to get better than that. Okay. Is that what you're trying to say?
Yes.
Okay. Did you get, I think one thing that's important is that your chief engineer should also be telling you that, hey, this is the weight goal that your
Mhm.
chassis needs to hit in order to um, meet our high level spec, because I'm sure you guys have a high level spec for
Right.
the weight of the car. So that's an important thing. Like a design judge in the competition, that's something they're going to ask about. So not just improve over last year, but it's like it contributes to the higher level goals. That's really important.
Hmm.
One other thing I wanted to add, I saw a lot of great testing. Like that's such a massive improvement upon like what we didn't do in I guess in years past. One suggestion I had about that and why it pertains to requirements is you do testing, right, to verify designs and therefore verify requirements. I think
Right.
one thing that's good is for the future is when you have requirements and specifications, maybe put it in like a table format where you have the requirement, you have a number, and then you have a verification method, and then you mention what the
Right.
test is. Because I think if someone isn't intimately familiar with your system
Hmm.
or the history of your vehicle, they might just see, oh, they're doing testing for the sake of testing, and and they don't have a reason. So like for instance, just might want to say, this is the testing method. This is why we're doing it. Like someone might
Right.
not understand why you're doing ping testing or hammer testing.
Hmm.
So I think that's a really important, table to have. And, I assume when you guys go to a competition, these are the, you're gonna show them this great testing and they're like, why are you doing this? And it's like, this is
Right.
exact, we're closing the design cycle. So,
Hmm. No, I agree with you. I agree with you.
but overall, really, really, really good job.
Thank you.
I'll let somebody else ask a question.
Please. Please have questions. I would love questions.
Hey, I have a quick question. This is Chaz.
Hi, Chaz.
Hey, let me see. I had two questions. Yeah, tag on
Great.
what Harris was saying. I really like that hammer test, and I think 2% is pretty good if I remember doing those tests. So great job. Um, to go to your fixtures, do you have that slide up? I know you
Yeah.
mentioned you had a few questions on that. Yeah, this slide's good. Um, So you were mentioning concerns of just making sure the tubes are always going to work with the hole size, or just wanted to see if you
Can
had
you
anything to
reiterate what
elaborate.
you said? Can you?
Huh?
You want to know what your concerns were with Oh, well, my concerns were okay. With the Yes. whole. Yes, yes. So my concerns, well, for one thing, for another big reasons why I want to do a pilot fixture, I was worried about the warping of the frame, but after like thinking this through myself, I think this just really comes down to having a more consistent welding plan for my welders and making sure they know what to weld next. Like make it easier for them to know what to weld next. So distribute the heat affected zone. But my concern was that for one thing, like the steering mounting tube and the lateral cross member on the bottom of the foot box, like I have holes for it where I would imagine, okay, I put in my fixture board. Now I'm gonna put through the steering mounting tubes itself, but what if it doesn't fit into the tube? So I think it really just comes down to making sure, like preventing any sort of warping having to happen because the thing is, not the entirety of the foot box isn't being remade, only partially. And that partially is, for one thing, the bent tube has to go. And in addition, something I got from um my welders is that they will love that they could just redo the weld from the steering mounting tube and the lateral cross member from the bottom foot box because if you were to just die grind it and take it out, just die grind and take out only the bent part, there is that gap between the steering mounting tube into the actual new tube that we need to put in. So for them, it will be much more easier to weld something with no gap than having to weld over a tube that already has a gap to begin with. So I think like my main concern is just like, what if nothing fits? Which is not really a concern, but I mean, it is a concern, but
Are
it's
you
something you
able to are you able to assign like a kind of angle tolerance to your tubes, or what's your tolerance? I know with frame it's kind of it's a bit of art, but
yeah,
there's obviously some tolerancing to it as well. I don't know. When you go out to mill some of these, holes for the tubes, I don't know. I would maybe do some test fixtures where you find out what hole size you like the best, programming into the CNC, especially because the CNC you could put in, half inch and then it ends up spitting out like 0.489 or something. So I know Mirror usually does that. So maybe do a few test pieces of different hole sizes and check the tubes. For looking at this fixture here, what's the sequence of, maybe I'm just not seeing it. What's the sequence of kind of putting the foot box together?
great question. I thought this through. So we're first gonna put in, so first we're die grinding and taking out all the tubes that needs to be cut out. So there's four tubes. Can you see my mouse, by the
Yep.
way? Okay, great. So we're gonna take out this suspension tube over here, this blue tube, then this green tube that's bent, then this lateral cross member on the bottom, and then finally the steering mount tube. So with that all taken out, that gives us room to put in all of our fixture boards in. So first we're gonna put in the fixture board. So we're gonna put in the lateral cross members, which
Hmm.
again which can go through the top because not only are we taking out these four tubes, we're also taking out this tube since again this has to be moved up an inch for ergonomics need to move your pedals back 2 inches. So this will be removed. So you have room to put in these lateral cross members first. Then afterwards, well, there is these slots. These slots is where the horizontal fixture boards will go, and those will be coming in from the bottom to the left.
Hmm.
So just imagine sliding in first. Then after that, we're gonna put in the steering mounting tube, and then finally also the bottom lateral cross member. And then finally we're gonna fit in this tube, which is the bent the bent tube. And then finally the suspension tube. And this is where I was bringing up with the second picture. So on the right, if instead of having a notch specifically for this, because we're going to laser cut the wood itself. The laser cutter can't cut it at an angle to account the suspensions like too. Like the angle matters. So for that, I was thinking, okay, we'll have a block, like we'll have a support system to hold the angle of the tube itself. And the notches itself would already designate like the placement of it, if that makes sense.
Okay. And then once it's all tacked together, are you able to pull them out, or do you just like destroy them, or?
We destroy it.
Oh, okay, that's fine as long as there's a plan.
Yes. The other thing was I was actually thinking about ways of actually taking it out. Like maybe let's say we can destroy it. I mean, we are able to destroy it, but let's say we can. Like, is there an easier way we could just like slide it in? But honestly, to me, I feel like this drawing is like the only solution in this case.
No, I was
So,
thinking that too. I didn't know for that front LC member if you're able to make a fixture. With
right.
those notches in the LC, all you really have to set is the height and just making sure it's horizontal. So you might be able to just get away with a slot there instead of, a hole. But it'll work either way. I mean, it looks like a good thing to try out. Do you think you can still do it like on the welding table?
Oh yeah, that's the plan. Like I want it to be on the welding table already.
Okay.
So it'll be easier for them to weld, especially. I wouldn't. So yeah.
Okay. Sweet.
Um,
Can I ask? It's a quick question. The green,
yeah,
I completely forget the member names, but the green
me
bent
too.
member, that's so that's currently continuous, and what portion of it are you removing?
Great question. So we're the bent member, that's entirely being removed. So
Oh wow.
we're
So
gonna
from all the way to the bottom to that
do the
the
top.
to essentially so that green member that's U-shaped, essentially it's getting completely removed from the very front green was it lateral cross member all the way
Yeah.
to the lateral cross member at the bottom of the foot box. And
Yes.
now you're going to replace it with like, not a similarly shaped part. Is that correct?
Yes. So
Okay.
it's still the same design that we have right now. So design wise for the foot box, nothing is being changed. But we still have to remake it because there's the bend.
I see. Okay.
And it has to be one continuous member, like you said.
Is this now I understand this fixture is just like a preliminary design, but is this are these two boards rigidly interlocked or are they two separate boards?
They're two separate boards.
Okay. Is like it was great that you're like I heard you guys were like thinking about sequencing of it, which is good. I think the other
Mhm.
thing that you might want to think about is like how you're constraining the tubes
Yeah,
and you're also thinking about like what are your critical members dim dimensionally
Mhm.
that you are more critical for being in positions for suspension and other mounting and
right.
use those as, I guess, your primary fixturing datums or focus more on establishing those because the way this is all sitting is that in order for this to all kind of go together, there has to be play in the system. It's going to jiggle.
Yeah,
This
yeah.
thing has to jiggle. So basically, you want to just think about like, hey, when you're doing this order wise, how do I actually, what has to go in first so that that's controlled and then everything else can kind of just get placed to fit. Otherwise, what's going to wind up happening is you might not make your suspension project team leads too happy if they're like, oh, this frame is not this member is not exactly where I want it.
Yeah, yeah.
Um, but I think you have a really good idea here. This is good because then you could also move the frame around to any
Yeah.
position the welder would like to get access to tubes. So I think it's a nice idea.
Any thoughts about the pendulum test, perchance?
Yeah, we could so let's look at the pendulum test.
Let's look at it. Okay.
So
Next slide, or I'll do this slide.
so let me ask this.
Mhm.
Um, okay, so you want to okay, front impact. I guess what is the key data point you would like to get out of this? Is I guess we
Well,
I know like in the past, like every single year, the team we all joke about taking one of the old cars and driving it into a wall, and we wanted to get the previous autonomous driving lead to hook up the car with stuff so we could drive it into a wall, but that never really panned out.
um, well, my goal was like just to have better understand the G-load for the front impact. Something that I got like definitely got ta like took points off from the last Carolina competition was one of the things they asked me was like, how did you get the G loads for the front impact and rollover? And I was like, well, I didn't. I use 3Gs because that's most commonly what the frame would experience. Like I would imagine the frame to experience a drop test like experience a drop more often than a rollover or a front impact. So my goal was to better understand the G load for the front impact, but also like possibly have a better understanding of like what force was needed to make the bench from the footbox. I think like overall with like testing for frames, I think there's like a lack of understanding of how these certain forces affect the frames overall. And I think like that's why I'm doing all the suspension testing, like to see like not suspension testing, but like the suspension analysis with the frame to understand how does the forces from there affect the frame.
Right.
So now how does the force from these external factors like a rock would affect the frame or like just
Right.
overall simulate that front impact FEA that we always use every year. So
Great.
that's the goal of this pendulum test. So I'm thinking like at this instantaneous moment that when it hits that wall, that's simulating a front impact test. So it's very theoretical because I'm saying at
So
this instantaneous moment is the
so
front
let's
impact.
so I think this is first off, I think it's great that you're finding these stable kind of test scenarios to run on the car that are repeatable and measurable. I think that's great. I think the one tricky thing here is you're trying to figure out, you've certainly thought about this a lot longer than I have. I've only seen this for a few minutes, but the one thing to think about is you are trying to see how a certain load case that you guys have during operation of the car affects the car.
Mhm.
But you don't you don't know this load case, right? Is that you don't
Mhm.
really know
Yeah.
what this load case is. You're assuming it's 3G. And I think with the pendulum test, you essentially what the drop height and the mass of the pendulum, this is kind of unless I'm missing something here at first glance, it's not that's still unknown. Another approach might I think the pendulum test might be good if you want to do a simulated crash test in the future when you know the load, but I think you
Mm.
need to think about how else you might find these loads. And I think you did something like that with your other tests where you're deriving it from real world testing of the car. So maybe you might
Right.
want to think about, hey, what are some cases during the race that you're getting frontal impacts either directly on the frame or
Mhm.
on the suspension or tires? And
Mm.
maybe think about if it's safe to do, of course, but replicating them with one of your vehicles that you already have rigged up with strain gauges and attempt to replicate it, whether it's driving into the suspension into a thick tree. I mean, sometimes this has happened by accident. We had during driver testing, or no, driver training many years ago, we had somebody lose control of the car and drive the front of the car into one of the light posts in the south side parking
Oh.
lot. So there's a
So
square
I think I
shaped
know what you're
indent in the front of the car. So obviously everybody was fine, but that would have been a great. I really wish we had load strain gauges on the car
Yeah,
because that's
yeah, yeah,
great
for sure,
data.
for sure.
Anyways, that I think provided you this is something safe you can do, think about ways you could derive these from real world scenarios and then gather the data and then show that hey, we have a um, this is the load case and we have a significant whatever a factor of safety that ensures the safety of the driver or whatever other requirements you might have to do. And then
Hmm.
and then you have that data point. Then you'll know what the accelerations are, right?
Yeah.
Maybe that's, I think you have a data acquisition team and then maybe go from there. I, did you, unless you guys had a way that you knew what mass you're trying to hit your car with this pendulum setup, is that something you figured out?
What do you mean by mass? Like, as in, like, Are you saying, because I'm envisioning it, I literally hit it towards Gavin Wall. Like,
He's
So
asking
you're gonna,
like lower position you want to have it from, like what acceleration you trying to achieve.
well,
oh,
are you gonna drive the whole forklift into a wall and just push the frame?
that was the idea.
Yeah, no, that's fine. Well, here's let's. I think also, I don't know if your chief welder's in there, but there's
Our
something
chief
called.
welder's in the meeting right now.
Okay, so
Yes.
maybe in material science class, you guys talk about impact toughness. You ever heard of something called the Charpy V-notch test? Is basically you take a piece of metal, right? That's you want to see exposing it to impact, and you essentially take like a pendulum, and it whacks into the side of this piece of material, and based upon the way the pendulum swings, if you look at a picture, it's a lot easier. It
Right.
tells you what sort of energy is imparted into there. That's when I saw a pendulum set up, that's what I was thinking, but
Okay.
I think I think the problem here is, there's unknowns and
Yes.
it's not clear to me like why like the amount like if you want to put energy into the frame just to see how the frame responds to a load case and maybe you could do a couple different load cases and look at the results from there, but um it just seems like it's difficult to connect that directly to
Yeah.
uh, a racing condition. But once you have a racing condition, you have as a data point, like for instance, that drop test that you guys do,
Mhm.
from racing that I guess your drop that all you need to do is survive a certain, depth of drop. You have it recorded, and now you don't have to go back out to the field anymore. You just do it in your parking lot with the forklift, right? You don't have
Mhm.
to go spend the time racing the car out there. So, um, I haven't been thinking about this problem very long, but it sounds like, and it's a challenging problem, but I think the first thing I would think about in summary is, hey, how can I pull something from a race condition? And then the judges can't argue with that. You say, hey, this is a race condition, this is a worst case for these reasons, and then
Mhm.
this is how we're going to utilize that. I think that's a good engineering rationale.
Okay. Understood. That's very helpful, actually. Thank you.
Yeah, no, really nice job thinking about these different tests. I mean, like this is I loved like the sketch, like all the sketches, all the pictures. This is really fantastic work.
Thank you. I like to draw.
That's great. That's great.
Okay. I actually have another question for everyone. Also, like, unless y'all have your questions, please feel free to say it. But I wanted to go back to the Chief Welders project. Like, I think the before I was a chassis lead, I was like also a welder for the club, and I'm really interested in how welding does affect the chassis overall. And I want to know in like what respect should we be looking into this test to make it like have like these data like be worthwhile for analyzing the overall chassis. Because I feel like obviously when we weld something, like it won't the yield stress would be less than what we would want it to be, like less than the materials yield stress. So I'm just trying to understand like well, I've been researching this for a while. Like for one thing, I hear a lot of debate of whether or not is it worth trying to analyze and see is analyzing how welding affects chassis really worthwhile. A lot of people say no, it's not. But then I think it is just because I do really like welding and it's something I want to do. So what can we take out from the project itself and like what should we look more into? I don't know if I'm phrasing my question right. I mean, I don't really have a clear question in mind, but what's something we should look out for when doing tests like these? If there's no
First,
answer, that's okay.
yeah, yeah, no, fair. I mean, first off, I'll say like analyzing welds is an extremely complex problem.
Mm.
So it's best not to make sure you don't die.
Yeah,
It's
we're not
very
an
interesting, but it can get very overwhelming very quickly. So I think it's important to kind of have like a clear objective. Um, First thing I'll ask is there, have you guys experienced a failure of a part, or um, do you have a very critical joint that you need in your design that's very critical for strength or lifetime? Like, I think those are some good questions to ask. Um, if you're just also just trying to do some verification to show that, hey, we have a consistent welding process. And, like one of the assumptions you're correct is like, when you're analyzing structures with welds is like a good like rule of thumb is in general a quality weld, the weld, the strength, sorry, the actual weld will be stronger than its surroundings. So you kind of saw in some of the testing, which is good for most things, many things. But if you just want to prove that that assumption is correct, and what that does is, you guys, don't need to, if you know that, hey, my welds are much stronger than my base material, then I don't have to do any fancy FEA analysis and hand calculations to figure out if my welds are going to perform.
Mhm.
I think that the way you can, that's like a big assumption we've always used. It's a good assumption, but if you want to like really prove it and show good verification, then maybe you could center your testing around demonstrating for different types of tab geometries, different types of welds, different loading configurations. So tensile, shear, compression, bending, that, hey, this is what we got performance out of our sample, and it kind of helps us to show that, hey, in all these different loading cases, our base material is failing before the weld.
Mhm.
So yeah, just I like it's a what welding strength of welded connections is a very complicated topic, especially if you want to start doing FEA of welds. And usually you only want to get into that kind of detail and complexity if it's absolutely necessary. So
Right.
I think start with the problem. These are the
Mhm.
problems I want to solve. So either you have failure or you're verifying an assumption in your analysis. Start there and then build the test.
Right.
Does
Noted.
that kind of
No,
help?
it does. It does.
Okay, great.
Mhm. Any other questions?
I saw you guys had a line there about do you want to do some fatigue analysis or fatigue testing, something like that?
Yes. I th- I feel like one of the well, I'm obviously just testing for this year. We've never done fatigue analysis on a frame, and I at least want to try it for the first time and see how that goes. I think a fatigue analysis would be really relevant for the mounting tabs that we have. Obviously, those would experience the most, like consistently experience this force every time we race. So I feel like doing a fatigue analysis there would be helpful. The other thing is, I'm not sure. I mean, I'm not sure if like, well, okay, because I was thinking of doing a fatigue analysis on on the footbox itself where there's the bend that happened, but that's really like like it was the bend was there because it fully hit a rock. I don't necessarily think it was because of fatigue that it made the bend that it made. But I think my question is a lot of this is just new, like how do I begin doing a fatigue analysis for frame, especially when we don't have like a number of, well, you give it a number of cycles. Sorry, I'm like thinking as I'm
No, that's
giving this
okay.
question.
Thinking out loud
But
is perfectly fine. That's good.
but I think what I'm trying to get at is where do we begin for doing a fatigue analysis on a mounting tab when you don't know the number of cycles, when you don't know like any of the necessary information you would need for those?
Okay. This
I
is yeah,
mean,
this is really good thinking. It's good to hear that you guys are thinking about these sorts of details. I think one thing, and this happens to everybody, is one thing is like don't put the cart before the horse. Like I mentioned earlier about testing.
mhm,
Testing are for verifying
the-
requirements and specifications. So there should be a requirement or specification. So now, if you're concerned about fatigue performance is, so that means you're concerned about lifetime of the frame or components. Is that reflected in your requirements and specifications?
no.
So, like for instance, you mentioned how a frame is rebuilt every 2 years.
Hmm.
That's a lifetime. So
Right.
maybe start high level, start with a requirement specification, break it down. So kind of break it down. Okay, a frame should be able to last 2 years of racing and testing. Okay. And then maybe do some kind of um, a little bit of math to figure out, how many hours racing it is, and maybe talk to your data acquisition team, and you figure out, okay, during amount of racing time, what sorts of maybe loads or cycles are we getting? Maybe focus on some really critical areas like, is there a certain area of the car that you're really concerned about, or it breaks off in the race? I remember for us, our front suspension would get beat the heck and just from the endurance racing and this and that. So think about the critical problems, like the things that are critical to your guys' success, and maybe if lifetime of components is important and you're seeing failures, then I think that's where you put the fatigue analysis in.
Mhm.
So so think about the requirements, think about the load, I guess the vehicle operation cases, and then get into the analysis.
Right. Hmm. Any other questions?
That's it for me. Really, really nice job, guys. Like really, really good job. Loved all the pictures and a lot of the detail, and the testing is fantastic. So really great to see how much you guys are able to accomplish.
You. Okay. I guess since there's no more questions, I'll end the meeting. So thank you so much for coming to my PDR. And I want to tell it to your friends too. So anyone, any Baham friends you still have right now, let them know. Let them know there's more PDRs. So tomorrow, is it 8 or 7? So at 7 p.m. is suspensions PDR. Wednesday at 8 is drivetrains PDR, and it's 7 p.m. on Thursdays ergonomics PDR. So really, thank you so much for coming to my PDR. It means a lot, especially if this is not a build season for frames. So, but all the feedback given really did help. So thank you so much, and tell your friends. Tell your friends. Anyways, yeah, thank you.
Do you wanna let your recordings and stuff on YouTube?
Oh, yes. Okay. To let you know, the recording will be posted on YouTube,
The link was already sent.
and the link was already sent out to everyone in the email to the YouTube channel. We have a YouTube channel. Make sure you subscribe. But yeah, thank you so much for coming. If you have questions or you thought about it, you really need to tell me, please email me. My email's in the first slide. So thank you so much. No, really, I do appreciate it. Like, truly, I do really appreciate it.
Yeah,
Okay.
really nice job. Looking forward to the other ones.